Okay, so our last section for this week is 10.2. This is also going to finish chapter 10, so we're going to be done with systems. And today I'm going to show you a different way to solve systems using a matrix. When you start to get into systems that have lots of variables, like 3 is not a lot, 4 is not a lot, 1,000 is a lot. Okay, so if you have 1,000 variables, generally that's something that a computer is going to solve. And a lot of people spend time trying to figure out how can we solve it faster. Okay, because something with 1,000 variables is going to take a long time for a computer to figure out. So there's all kinds of things people spend time doing to learn how to do it faster. Okay, we already know how to do it, but the thing is we want to do it faster. All right. So the method that I'm going to show you is a very systematic approach. It works well for human brains because you do the same thing every time in exactly the same order. The method that works well for us does not work as well for computers. Okay, this method is kind of slow for a computer, and a computer can do it much faster than the method I'm going to teach you, but it wouldn't make any sense to our brain. It would do all kinds of weird things to speed up the process that just don't make sense to us. So we're gonna learn a method that works well for us. This one, I think I'm gonna skip over this one, so don't worry about this one. I want to just jump right into what's a matrix. Okay, so from yesterday we were using elimination and we were writing out the entire equation, all the letters, all the numbers, equal sign. Now we're going to transition to using a matrix. So I talked a little bit about a matrix yesterday, but basically a matrix is just a fancy word that describes like a spreadsheet. It has rows and it has columns. What can you put in the rows and columns? We're going to put numbers, but you could put anything. You could put names of people, and I think I made a connection with the sign in, sign out thing I have. You could have colors, you could have part numbers, you could have anything in a matrix. And in particular, our matrices are going to be two-dimensional, rows, columns. Matrices can also be three-dimensional. So that's a little more complicated, but almost imagine like a building with different rooms in it, all stacked on top of each other. You could be in, the front of the building, one floor down and one floor to the right. Or you could be in the back of the building, one floor down, one floor to the right. So you can start to get into a 3D matrix, or as many dimensions as you want, really. So the way we describe a matrix is by its dimensions. You always list the rows first and then the columns. So you might have a 2x4 matrix, 2 rows, 4 columns. 5x5 matrix, 5 rows, 5 columns. The last type I told you, 5x5, if the number of rows and the number of columns is the same, that's called a square matrix. We also want a way to reference a position in the matrix. All right? So I'm going to show you the notation and how we are going to reference a spot in the matrix. And then I'll show you, or I'll at least tell you, how a computer does it, which is a little more complicated. But each thing that's in the matrix is called an element. So you might want to know, what's the element in row 3, column 6? Well, what's in that spot? Okay. That spot is called, it's an element in the matrix. So if this was our matrix, this is a 3x3 matrix, 3 rows, 3 columns. The convention in our book is to name a matrix with a capital letter A. And when you want to reference a specific element in the matrix, you use the same letter that the matrix is named, but you use the lowercase version. So A sub 2, 3 stands for the element in row 2, column 3. So if I look at the matrix, row 2, column 3 has a 9 in it. Okay. On a computer, okay, the way you would reference that is, well, you have the name of your matrix. And on a computer, you can name it anything you want. It doesn't just have to be a capital letter. You could call it part numbers or colors or ages. You could call the matrix name whatever you want to call it. And you would do something like this. Right? At least in some computer languages, that's the notation for picking out the element in row 2, column 3. Kind of. This gets a little tricky with computers because computers don't start with row 1 and column 1. They start with row 0 and column 0. So that can get a little confusing if you do it that way. Whenever I did matrices on a computer, I never used row 0 and column 0. So I always had a bunch of blank spots in my matrix. I would start with row 1 and column 1. Because then what you're thinking in your mind, okay, the second row is actually the second row. If you don't do it that way, and you use what's in row 0, then this would actually be row 1 that I just pointed to. Okay, and that gets a little confusing to keep track of. So some things are a little different on computers. Yeah, question?
Why do they have a lowercase when you're writing it, but the thing is like called capital one?
Just to differentiate in our textbook, the matrix itself from an element in it. Another thing about matrices on computers is they can take up a lot of space, right? You've got, let's say you had 1,000 by 1,000 matrix. Okay? 1,000 times 1,000, that means you're setting aside a spot for 1,000,000 elements. That's a lot of elements, depending on what you're putting in them. If it's just a single number, maybe it's not bad. But pretend each element had a sentence in it. For whatever reason, you're storing 1,000,000 sentences. That's a lot of stuff. So a lot of times what we can do, at least on a computer, is we can have these kind of things, what we call dynamic. So they change size based on what we need. So if we don't have enough room, it gets a little bigger. If we've got extra room and we're not using it, the computer can shrink it down and say, you know what, I don't need the matrix as big right now. I can make it bigger later if I need to. But right now, I don't need it that big. So I'm going to shrink it down. Okay, so any questions on that? All right, so let's keep going. So we're calling it a matrix. A lot of times when you work with it on a computer, they call it an array. Same thing. But one advantage of using an array or a matrix is we don't have to write the letters when we're solving equations. So we're going to be using a matrix specifically as a short way of solving an equation. That's one of probably thousands of different things you can do with a matrix. Okay, and I might have mentioned yesterday that if you really are interested in matrices, there's an entire class on it in college called linear algebra. All you do is stuff with a matrix. If you're interested in any kind of like game design, like programming and writing code where you design a game or design something that is visual on the computer, like that somebody interacts with, matrices is how you do all your transformations. So like let's say I had a book and I wanted to take the book and rotate it on the screen. A rotation is done with a matrix. It uses sines and cosines, and it's a little complicated, but that's how it's done. So matrices are used a lot when you draw stuff. So for our matrices, we only need to write the coefficients of the variables. What's important is that we line everything up. One column is going to represent one variable. Okay. Conventionally, the first column is the x's, the second column is the y's, the third column is the z's. I would stick with that. Okay. But most importantly, you've got to have all the same letter in the same column. So I'm going to show you in a second how to kind of start this. And the matrix that you set up that has all the coefficients of the variables in it is called the coefficient matrix. But remember that the coefficients aren't the only thing in the problem. Okay, you might have something like that. You have a 2, an 8, a 3, a negative 12, but we have to add something onto the matrix that represents the two numbers on the other side. So what we're going to do is, once we put these 4 numbers in the matrix, we're going to add one extra column to it with a 5 and a 2. That represents the constants on the other side of the equal sign. And generally, the way we do that is we put a vertical line in the matrix just to separate what's on the left side of the equal sign and what's on the right. Because once you put it in a matrix, you don't have an equal sign anymore. But we want people to remember what was on the right and what was on the left. Questions on that? So let me go back up and just show you how I would put all of that in the matrix. I'd have a 2, 8, 3, a negative 12. And then I would put a line just so we can remember where the other side of the equation was, a 5 and a 2. Now, even though I'm going to show you one way to solve equations with a matrix, there's actually several ways to even use a matrix to solve systems. We're going to look at what's called Gaussian elimination. So we can do that. We can also do Gauss-Jordan elimination, which is a little different. If we have time, maybe I'll show you one like that. But yeah, there's different ways to use a matrix to do what we're going to do. But in Gaussian elimination, this is the goal. You want to transform your coefficient matrix, this matrix right here, so that you end up with 1s on the main diagonal. Okay, the main diagonal goes from upper left to lower right, and 0s below it. Okay, that's the goal. Now, you might be doing a 2-variable 2 equation. You might have 3-variable 3 equation. You might have 5 variables and 5 equations. You're not in this class, but get 1s on the main diagonal and 0s everywhere below it. And there's a couple names for what this is called. The process is called Gaussian elimination because you're eliminating everything that's down here and turning it into 0s. Once you do that, your matrix is now in what we call row echelon form. Another name for row echelon form is lower triangular form. You might be able to guess why, because in the lower part of the matrix, you're forming a triangle of all 0s. So just to kind of keep the vocab straight, Gaussian elimination is the process of creating a matrix in row echelon form. And it's called Gaussian elimination because it's named after somebody with the last name Gauss, G-A-U-S-S. Questions on that? All right. So to get something in row echelon form, there's certain rules you have to follow. Certain things you can do, certain things you can't do. So in order to get row echelon form, you are allowed to use what are called the elementary row operations. The first thing that you are allowed to do with any matrix is you can swap two rows. Basically, swapping two rows is the equivalent of just changing the order the equations were given to, just swapping the rows. The notation that I'm going to use to swap rows, like let's say you wanted to swap rows 1 and 2, I would write it like this. That means to swap rows 1 and 2. So anything with a circle around a number is going to represent a row. You can also multiply a row by a non-zero constant. That should look familiar from what we did yesterday. Sometimes you had to multiply an equation first and then add it to get the numbers to cancel. That's what rule 2 is. So let's say you wanted to multiply row 1 by 5. I would write it like this. And that's exactly the notation I started using yesterday. Okay. And the last thing you're allowed to do is to add one row to another row. That's something we also did yesterday. So we did something like row 1 plus row 2. Or maybe we did something like 2 times row 1 added to row 3. Okay, those are the only 3 things that you are allowed to do that will not affect the answer to a system of equations. Okay, so you can't swap columns, definitely can't do that for what we're doing. Okay? But you can swap rows. Questions on the 3 elementary row operations? All right. Okay. So let's look at an example. This was the first example in the notes. I didn't feel like we needed to do it the old way, so we're not really solving it again. We're just solving it for the first time using a matrix. Now, one thing is, depending on how you write, matrices can take up a lot of space on the page. Especially if you only do one calculation per step. That's the easiest way to do it, so you don't lose track of what you're doing. But if you only do one calculation per step, you're going to end up copying a lot of stuff over that's not changing in each step. All right, so first thing I'm going to do is just translate this all to numbers. In the first equation, what's my coefficient of x and z? Because I don't have a number there, but I got to put a number in the matrix. They're both 1s. So I'm going to start with 1, -2, 1, -1. Now, sometimes people put those little brackets around it for a matrix. You don't have to put them. I'm fine if you don't. I don't think the book uses them as much. But definitely put that vertical line in. Okay? All right, so 2, 3, -2, -3, 1, 3, -2, -2. You're doing so much copying. You have to be very careful you copy it correctly. Okay, so if you notice that I copy something wrong, please let me know. All right, let me kind of go through the general order. So the goal, as we said, is to get 1s on the main diagonal and 0s below. You have to do that in a certain order. Okay? I'm going to number the order to do it in right now. First, you get a 1 there. The second thing you're going to do is get a 0 there. The third thing is we're going to get a 0 there. That will complete the first column. Then we go to the second column. So we work across the columns. That's how this method works. We work down and across. The fourth thing we're going to do is get a 1 there. Then we're going to get a 0 there. Okay, I'm not going to write those little numbers circled each time, but those are the numbers we're going to tackle in that order. A 1, a 0, a 0, a 1, and a 0. And if we're really going to finish it out fully, the sixth thing would be to get a 1 right there. That step is kind of optional because once you've gotten to that point, you're pretty much done the problem. So we'll look at it. So you might notice as you do it, like, let's say you already had a 0 in this spot. That doesn't help you at all because you have to go in this order. And what I'm probably going to end up doing is I'm going to be messing up that number before I get to it. Okay? Because I've got to get to the top left first, then the 2, then the 1, then the 3, then the other 3. I can't go out of that order. All right, so let's start with the top left. I already have a 1 there. So nothing I need to do this time. If there wasn't a 1 there, I would fix it so there is. Like, don't write it down, but if this was a 2, I would multiply everything by a half. And that would give me a 1, -1, and so on. Okay, but I don't need to do that this time. Okay, second thing. I want to get a 0 right there. To do it, I always use the equation that's above. So what would I have to multiply equation 1 by, and then add it to equation 2 to get a 0 where I circled? Yep. -2. -2. So we're going to do -2 times the first equation. We're going to add it to the second equation. And we're going to replace what is in the second row with that calculation. So what on the left is the calculation we're going to do. On the right is where we're going to put it. Okay. All right, so we'll do that. And let's do another one at the same time. What would I have to multiply equation 1 by, and then add it to row 3 to get a 0 there?
Pardon my interruption.
Okay, so what would I have to multiply equation 1 by? And then add it to equation 3 to make a 0 in what I called the third spot. Yep.
-1.
Yeah, so we're going to do -1 times the first. That's just something mental we're going to do in our head. We're not going to write that down. We're just going to do -1 times the first. We're going to add it to the third. All of that's going to be in our head. And then we're going to write that answer down and replace what's in the third row now. Okay, so let's do that. What I'll do to save a little space, you don't have to do it this way, but I'll put a matrix, the calculation, and then the new matrix. If you did it below, that's fine. Just keep doing it below. All right, top row stays the same. 1, -2, 1, -1. Now, let's carefully go through the calculation. -2 times the first, added to the second. What's 1 times -2? Plus 2. 0. -2 times -2? Plus 3? 7. 1 times -2? Take away another 2 is -4. And -1 times -2? 2. Take away 3. -1. Okay, so there's our second row. All right, let's do the third row. -1 times the first added to the third. So 1 times -1? -1 plus 1? 0. -2 times -1? 2 plus 3 gives me 5. All right. Let's keep going. So we've got 1 times -1 is -1. Take away 2 is -3. And the last one, negative 1 times negative 1 is 1. 1 take away 2, negative 1. Yeah.
Is it just a coincidence that all the endings ended up negative 1, or is it supposed to?
Yeah. No, it just happened. Yep. Okay. Any questions on that? Okay, so now let's look at the next step. What I want to do first is I just want to double check because I really don't like that 7 there. It's not that we can't do it, it's just we're going to get some fractions. So I want to just make sure that I copied it. 1, negative 2, 1, negative 1, yep. 2, 3, negative 2, 2, 3, negative 2, negative 3, yep. 1, 3, negative 2, negative 2. Yep, it's just the way it's going to go. All right, so the first column is done, and the first row is done. You never want to use the first row again, because if you do, if you take anything in the first row, any multiple, and add it to the second or third row, what would happen now? Yeah, you're going to mess up the zeros. So you can never use the first row again. What you can do is now you use the second row. Okay? Because if you use the second row and you add it to the third row somehow, you will not mess up the 0 in the first spot because it has a 0 as well. All right. So we want to get a 1 right there. There's a couple ways we can do it. We could multiply everything by 1/7. Okay, so that's going to lead to a little bit of messy fractions. Another thing you could do, and it wouldn't make it a 1, but it would make it closer, is if you multiply row 3 by negative 1 and add it to row 2, what would it make the thing that I circled? It wouldn't make it a 1, but it would make it, yeah, it would make it a 2. And then if I had a 2, all I would have to do is multiply everything by a half. To me, that's a lot easier fraction to work with than sevenths. But we can do it either way. So do we want to multiply everything by 1/7? Or do we want to multiply the bottom row by negative 1, add it to the top, and then multiply through by a half? Well, Leo, any thoughts on which way you want to do it?
Probably multiply by -1.
Okay, so that's just a little trick to try to make that number closer to a 1. I wish I could make it exactly a 1 somehow, but I can't without multiplying that row by a fraction. All right, so let's take, first row is going to stay the same. We're going to take -1 times the third row, and we're going to add it to the second, and we'll replace what's in the second row. We'll just do that in this one step, and that's it. Right, and I'll put the calculation right below it to try to save a little space. So 1, -2, 1, -1. Now the bottom row stays the same. And the middle row, that's going to stay as a 0. Multiply 5 times -1 and add it to 7. Okay, that's better. Now we have a 2 there. -3 times -1 is 3. 3 take away 4 is -1. And multiply this by -1. We get 1 combined with a -1. Get a 0. Now, when I multiply the second row by a half to get a 1 right here, my numbers are so much cleaner than they would have been if I had multiplied everything by 1/7. But either way, we'll get you the correct answer. Any question on why we did that? All right, so now again, I'll just do a single step so I don't lose anybody. Well, hopefully I haven't lost you yet. I'll just multiply row 2 by a half. That's it. Okay? It's going to mean I got to do a lot of extra copying, but I think it'll be easier to follow. Let's take row 2, multiply it by a half, and we're going to replace what's in row 2 right now. Okay? separate this off too, so. All right, so row 1 stays the same. Row 3 stays the same. Mentally, I just like to copy over the stuff that's not changing, rather than like do some of the stuff that's not changing, then do some calculations. Bless you. Then more stuff that's not changing. Just copy the stuff that's not changing, get that out of the way. And now let's multiply everything by a half. 0, 1. We still get a fraction there, but that's not bad. We can deal with -1/2 better than we could have dealt with -4/7. So, and then the last number is 0. So by doing it that way, we kind of avoided some really bad fractions. Okay. Any questions on that step? So now we've got the 1, we've got the 0, we've got the 0, we've got the 1. I want to get a 0 right there. But because I have a 1 above it, it should be pretty easy to figure out what to multiply row 2 by. Okay. What would you multiply row 2 by to make a 0 in the spot I circled? Yeah. -5. So we're going to do -5 times the second row. We're going to add it to the third row. And we're going to replace what's in the third row right now. So is row 1 changing? Nope. Is row 2 changing? Megan? No. We're not replacing anything that's in row 1 or 2, just row 3. This calculation right here, that's all in our head. We're not going to write any of that down until we get to row 3. Okay. So let's copy over the stuff that's going to stay the same. Row 1, row 2. And now let's do the calculation. What's 0 times -5? Plus 0? 0. Thank you. Is that? Yeah, forgetting a negative is really bad, but just be careful. All right. 1 times -5? Plus 5? 0. Good. Negative times negative is positive. What's half of 5? 2.5. So you could write it as 5 halves, or I don't know. I think the decimal is easier to think about. And then the last one, 0 times -5 is 0. Take away 1. -1. All right. Now, I said getting a 1 here is kind of optional, and I usually hold off on that part because we're basically done. Okay. I know we don't have any answers yet, but we've done 90% of the work in this problem. What does this last row say if you translated it from a matrix back to an equation? Yeah?
2.5z equals -1.
Yeah. It says 0x plus 0y plus 2.5z equals -1. Now, we can easily solve for z just by dividing. So that's like dividing by 5 halves, so it's multiplying by 2/5, so that should be -0.4. If I did that right? Yeah, -0.4. Okay, let me just double check, make sure. They got a different answer. So, yes, small mistake, hopefully fixable very easily and quickly. Yes?
You added the negative. You didn't add the -3 to the 2.5.
I didn't add the -3 to the 2.5. Perfect. That was the mistake. So hopefully the phone doesn't ring during your test. So you multiplied by -5, right? We multiplied -5 times that negative a half, and we got 2.5, but then we didn't do 2.5 minus 3. So what's 2.5 minus 3? Negative 0.5. And this is the answer that we've got. So now, it's a good thing the mistake we made was at the very last step we just did. Otherwise, the mistake could have been way earlier. So now the last row says that equals negative 1. So z is 2. And that's what the book got. Now that we know z is 2, you work your way back up. What does the second row say as an equation? Y minus a half z equals 0. Okay, so let's look at what we got. Y minus half of z. Well, z is 2, so half of z is 1. So what's y? Y equals 1. Yes, that is correct. So we got z, we got y. Now go back to the top row, and we can find x. So that says x minus 2y, x minus 2, plus z, so plus 2 equals negative 1. Well, plus 2 minus 2 cancels out, and you're done. X is negative 1. Okay, I would say that one is probably, in terms of the ones that I'm going to give you, a little harder than average because of this tricky step here with having a 7 and having to deal with that. Okay, sometimes you have a couple options, but I think the way we did it was pretty good. Okay, any general questions on the kind of the steps, like the flow, the way we did that problem? Okay, let's try, well, I got 2 more. We don't have to do both. Let's do, I guess let's try this one. Now, one thing I'm going to mention, I haven't gotten to it yet, is that you can end up with a no solution or infinite solutions with a matrix. We're not going to be looking at those cases, but basically what would happen in a no solution or infinite solution is you'd be going through the matrix, and all of a sudden you'd end up with something like this. You'd end up with a row of all zeros. That would be an infinite solution. 0 equals 0. Or you end up with something like this. 0x plus 0y plus 0z equals 8. If somehow you ended up with that and you did all your arithmetic correct, that's a no solution. Okay? So those things can happen, but not in the problems I'm going to give you. Okay, so I want to write this as a matrix, but I don't think I want to write it in the order they've given it to me. Does anyone have an idea of what I could do right away, just to save having to copy this all over an extra time? Well, what's the first thing that we want to do in the matrix? We want to make sure that we have a what? Where? Yep.
A 1 in the top left.
A 1 in the top left. If you copy them down in this order, you will not have that. Is there any way I could get that? Well, I mean, there's lots of ways I could get that. I could say, all right, well, let's multiply the top equation by a half then. But there's an easier way. Yep.
So should I do the first and the second?
Yeah, let's just swap rows 1 and 2 right away. We won't even write down that we're doing it. We'll just do it before we even create the matrix. So let's put 1, 3, negative 1, negative 3. So that's now the top row. And let's put the first equation as the middle row. 2, negative 1. Wait a minute. What about z? What do I put for that? 0. The fact that I have zeros here doesn't do anything for me. Might make some arithmetic easier, but I don't really care that there's zeros there. And then the third row, that does help me. That's huge, right? Because I already have a 0 in this spot, and that will help me a lot. So 0x, 3y, 1z, 8. There's another name for a matrix if it has a lot of zeros in it. Like let's say you had 1,000 rows and 1,000 columns. So that's 1,000,000 entries. And let's say out of those 1,000,000 entries, 800,000 of them were zeros. So only a couple 100,000 were numbers, but 80% of them were all zeros. That's called a sparse matrix. And computers can deal with those kind of matrices faster because there's so many zeros all over the place. And they can help the computer speed up the process. Okay. It'll speed it up a little bit for us, but just coincidence, we got a 0 there right away, so that's good. All right, so we already have the 1. We already have the 0. I need to get a 0 right there. Okay. So what would be the number I'd have to multiply by to make a 0 in that spot? Leo?
The first row by -2.
Yep. Multiply the first row by -2. That's not something we're going to write down. That's in our head. We're going to add it to the second row. And then we're going to replace what's in the second row, and we're going to write that down. So which rows are not changing in this case? Yeah?
1 and 3.
1 and 3. So let's just copy them down so we can keep our brain in copy mode rather than arithmetic mode and just copy what we see. So we got 1, 3, -1, -3. So right now my brain is kind of off. I'm not even thinking. Just copy. 0, 3, 1, 8. All right, now I got to turn my brain on and start thinking about calculations. So -2 times the first added to the second. What's -2 times 1? Plus 2? 0. -2 times 3? Minus 1? -7? 7s keep popping up. I don't like 7s. -1 times -2? 2 plus 0 is 2. -3 times -2? 6 plus 0? 6. Okay, so we have kind of the same options we had last time. We could multiply row 2 by 1/7, and you're going to get 0, 1, 2 7ths, 6 7ths. Or, I think this time we can get this number even closer to a 1 than we did last time. Does anyone see what I could do with row 3? But it wouldn't make it a 1, but it's going to make it so close that we're only going to have to do one thing to make it a 1. And we're going to be able to avoid fractions for now. I'm not saying the answers might not get fractions eventually, but for now we can. Yeah?
Multiply the bottom by 2.
Yeah. If you multiply the bottom row by 2 and add it to the top row, watch what's going to happen to row 2. Okay? I wish this middle number was a 2 instead of a -7, because if it was a -2, I would just multiply everything by a half and it would be beautiful. Right? If that was a -2, you'd get -1, 1, 3, done. But it's not. So we're just trying to work around it for now. All right, so row 1 stays the same. Row 3 stays the same. 2 times the third row added to the second. Well, 2 times 0 is 0, plus 0 is 0. What's 3 times 2? Take away 7? That's great. If you got a -1 there, that's almost as good as having a 1. Pretty good. All right, 2 times 1 is 2, plus 2 is 4. 8 times 2 is 16. 16 plus 6 gives me 22. All right, now, what would I have to do to get a 1 in the second row? Yeah.
Multiply by -1.
Yeah, we just have to multiply everything by -1. So if you wanted, we could just change the signs of everything in the row, or we could write it out and copy the whole thing again. I'll write it out so you can see it. But it's kind of a waste to copy the whole thing all over again just to change the signs. But if that's the way we need to do it, to keep track of what's going on, that's fine. All right, so change the signs of everything in row 2. 0, 1, -4, -22, 0, 3, 1, 8. Now, the whole reason we got a 1 there is because it's going to make it easy to figure out what to multiply by to get a 0 there. What would we multiply row 2 by to create a 0 in the spot that I've circled? Yep. -3. So we're going to do -3 times the second, and we're going to add it to the third.
Can we just use row 1 and multiply by -1, or does it have to be row 2?
What would happen if you multiplied row 1 by -1?
Never mind, it was messed up.
It would mess up the zeros. So you would get a 0 in the spot we want, but then you would mess up the other 0. So yes, we always work kind of down and to the right. Once you're done with column 1, you're done with row 1. Don't ever go back to it. We're in column 2. Now we're using row 2. Okay. All right. Okay, is row 1 going to change? Nope. Is row 2 going to change? Let's just copy those first. 1, 3, -1, -3, 0, 1, -4, -22. Now we got to do this out. The first one is easy. 0 times -3 is 0, plus 0 is 0. 1 times -3 is -3, plus 3, 0. -4 times -3, 12, plus 1, 13. I really hope this is like a 26 or a 39 or something nice. 22 times -3. 66. And what's 66 plus 8? 74. All right, so now the last row says 13z equals 74. So how would I get z by itself? Divide by 13. Well, if you check, 74 divided by 13 is that. So that's how we're leaving our answer. So answers don't always come out nice. Doesn't mean you made a mistake, but as I said, for the test, I would expect to get nice integer answers. All right, so we've got z. And now you just work your way back up. Abby, what does the second row say as an equation?
Y minus 4z equals -22.
Y minus 4z. So 4z is 74 times 4. So that's 4z equals -22. Okay, so I'm going to use the calculator to handle all that for me. So I've got -74 times 4 divided by 13. And I'm going to add that number to -22. So -22 plus the fraction I just calculated. And by doing it this way, I'm not doing any rounding, the calculator can actually give me the fraction. Okay, because I don't really want to have to deal with common denominators and all that. So I just did it all in the calculator, press math, fraction, and it's -582 over 13. Pretty awful answer. So we got y. And then the last row, we'll plug in and get x. So x plus 3 times y. That's 3 times y, yeah?
You made a mistake.
No.
Instead of adding a positive for x, you subtracted it. Or
Positive 4x.
Well, when you moved it to the other side, this sign was wrong.
So negative 22 plus, oh, it did negative, it basically subtracted it, didn't it? Yeah, so it should have been negative 20, I gotta type it in again. So it was negative 74 74 times 4. That's the numerator, divided by 13. And then we want to add 22 to the other side. So it was negative 22 plus, how can I do this? I want to add 22.769, but I don't want to round it.
Just negative 8.
Yeah, if I just do plus the negative of my answer, that's awful. There we go. And convert that to a fraction. 10/13. Thank you. All right, that's actually going to be a little nicer to work with. So I hope the process is seeming okay, even though these numbers are pretty awful towards the end. I just hope the process of getting the 1s and 0s is what you got out of this one. Okay, don't get tripped up with all these denominators of 13. It's just the way this one worked out. All right, so we've got x plus 3 times y minus z, so minus 74 over 13 equals negative 3. All right, I'm going to do a little bit of this out because it's too much to type in for me all at once. So it's x minus 30 over 13 minus 74 over 13 equals negative 3. I'm going to combine those together. So negative 30 over 13 minus 74 over 13. And again, I could probably do some of that in my head, but it's just easier to let the calculator do it. So you get negative 8, which is surprising. Right, I'm just going to double check. We had negative 30 over 13 minus 74 over 13 equals negative 8. Any question on that stuff? Seems okay. So as long as we did all that right, what does x equal? Yeah, 5. Okay, so besides the kind of the ending part of this problem that was a mess, any question on just the matrix stuff above that line? Just getting the 1s and 0s. Okay, if you can get the 1s and 0s, I wouldn't be as worried for the test about crazy answers like that. It's not going to happen. Okay, and in the next class, I'm probably going to try this problem instead. And see if it comes out nicer. In fact, I think that's the one I wanted to do with you guys, and for some reason I did this one. Oh well. All right. So as I said, we're always going to deal with the single solution. You're never going to have multiple solutions to look at. And the homework, not every problem is a matrix. That would take forever. I think 1 through 6, there's nothing to do with matrices at all. It just basically says, tell me what's in row 2, column 3. So you just have to write like single numbers. And then don't worry about 32. Okay? So 1 through 6, 17, 18, 21. I think those are 2 variable problems. 24 and 31 are 3 variable. Okay, so don't forget, I'll be after school today. If anybody needs to finish anything up or needs extra help. And we'll have our second to last test for the term on Friday, tomorrow.